A very good afternoon to all of you. First, can you tell me whether you all can see the screen clearly and can you hear me clearly, please? Okay. Okay, so let's start. So today we are going to do the past paper MCQs from the years 2017 to 2021 of the second lesson of your A-level syllabus, which is structure and bonding. So first, now when you all take the A-level paper, the first part consists of 50 MCQs, right? To be done in 2 hours. So when you roughly divide 2 hours by 50, for one question, the time you roughly get is 2.5 minutes, right? But structure and bonding, if you know the theory to the point from the basics, and if you have applied all the questions, and if you have applied all the shortcuts and done the past paper questions for like about 10 to 15 years, then for sure you will be able to do it within a few within a few minutes. So that will enable to save time for the other MCQs like physical chemistry or any other challenging MCQs which you all will be having when you all are doing the A-level paper. So structure and bonding is a comparatively easy lesson if you all know the basic and the theory to the point and the shortcuts in order to do the MCQ. So I hope you all have done the questions. If you all have done these questions, then good, very good. You all can correct it as we go. If you all have not done, nothing to worry. You all can listen to I will take you all to the question first and then explain the answers one by one. So please follow with me and give me your full attention and full focus. Be very concentrated in this session, throughout the session. Then I'm sure by the end of the session, you will be able to finish the structure and bonding MCQs of your A-level paper. For each question, you will be taking about 30 seconds. You all can finish it in about 30 seconds. Right? So be very focused and give it your full attention, please. Okay. So we'll start with the first question. 2017. These questions are from the 2017 paper. Right? So the first question is, which of the following statements is false with regard to the following molecules? And they have given us some molecules. So the first statement is, all molecules have polar covalent bonds. Now, please be notified that this is false. Okay, you all have to select the false statements. From these 5 answers, you all have to select which is false. So the first one is, all molecules have polar covalent bonds. Now, what are covalent bonds? I'm sure all of you all know by now what are covalent bonds. Sharing a bond that is formed when a pair of electrons is shared between 2 atoms. That is called a covalent bond, right? So covalent bond, there are 2 types mainly. One is polar covalent bond and the other is the non-polar covalent bond. Now, what is polar covalent bond? Polar covalent bond means there is the electronegativity difference. The atoms which are joined by the bonds are different. That means their electronegativity are different. So they are having an electronegativity difference between the atoms, right? So in this case, carbon dioxide, oxygen, if you take the carbon-oxygen bond, not the entire molecule, we are considering only the bond, carbon-oxygen bond, right? So if we consider, now see here down, carbon-oxygen double bond. Oxygen is more electronegative than carbon. Oxygen is having 3.5 electronegativity. Carbon is having just 2.5 electronegativity. So there is an electronegativity difference. That means what will happen? The electrons in the bond will be more right? So will the electrons be equally shared in the bond? No, electrons are not equally shared. They are more towards oxygen. That means it is having an unequal sharing of electrons here. Can you see my mouse pointer? Is it visible? Okay, I hope it's visible. If it's not visible, my mouse pointer, please let me know. All right, okay. Okay, so there should be an electronegativity difference. If there is a electronegativity difference, we call that bond as polar covalent bond. Non-polar covalent bond means same atoms are joined by the bond. Same atom means oxygen. This oxygen also has the electronegativity of 3.5. This oxygen also the same electronegativity, 3.5. So 3.5 minus 3.5 is 0, right? So electronegativity difference is 0. So if that is happening, that means the electrons are equal shared for both the oxygen. It is not getting pulled towards one atom, right? So then it is a non-polar covalent bond. Now in all the examples which is given to us in all the molecules, carbon dioxide, the carbon-oxygen bond is a polar covalent bond. BF, it has an electronegativity difference, so it is a polar covalent bond. This is the plus pole and this is the minus pole. If the atom is more electronegative, that means the electrons are getting attracted to the more electronegative atom now. So then there will be a partial negative charge around that atom. That is only indicated by simple delta letter. Simple delta minus means more electrons are attracted, so the higher partial charge will be there. A negative partial charge will be there. I'm sorry, not higher. It is negative partial charge. And boron, now boron's electrons will be taken away from boron towards fluorine, right? So boron does not have enough negative charges around it. So what charge will it be getting? It will get a partial positive charge. That is indicated by simple delta plus, right? And then the dipole moment is always going from delta plus to delta minus. That is a fact. I hope you all know it by now. So dipole moment is indicated like this by the arrow. It is going towards the more electronegative atom, right? Those are few extra things here. So now all these molecules are having what kinds of bonds? Polar covalent bonds. Is that clear to everyone? Okay, I hope it's clear to everyone. So, because all of them are having polar covalent bonds, the first statement is a correct statement, right? All the molecules have polar covalent bonds. First one is correct. I'm going a bit slow at the first and then I'll be speeding up as we go. If there's any point that is not clear or if I'm going too fast or too slow, please let me know at once, okay? Okay. So then, the second statement, all molecules have different shapes. Now we have to see about the shapes. So now the traditional method, what is the traditional method to find the shape of a molecule? Using the VSEPR theory, valence, shell, electron pair, repulsion theory. That is the traditional method. Okay, so you have the carbon dioxide molecule, take the electrons from the carbon. Now, there are 4 electrons which is given to the bond by carbon atom. And from one oxygen atom, how many electrons are given to this bond? 2, right? So there are 2 oxygen atoms. So 2. From totally the number of electrons given to this molecule by the oxygen atom is 4. So then when you add these two, the total number of electrons in this molecule will be, in the bonds, which is shared in the covalent bonds will be 8 electrons, right? So then 8 divided by 2, by 2, the number of repulsive units around the central atom. What are repulsive units? The bonding electron pairs and the lone pairs, right? So number of repulsive units are 2. So 8 divided by 2, 4. So if there are 4 repulsive units and there are 0 lone pairs, the shape is tetrahedral. So that is how we usually take from the VSEPR theory. That is the traditional method to get the shape of a molecule. I hope you all know that by now. If not, I hope you all got it, what I said, okay? So there's a shortcut to determine the molecular shape, right? So this I recommend you all to do for the MCQ questions to save time. First, count the number of repulsive units. Now, if it is carbon dioxide, we'll take carbon dioxide. Count the number of repulsive units around the central atom. What is the central atom? Carbon. How many repulsive units? 1, 2. Repulsive units means what? The bonds and the lone pairs. Single bond or double bond or triple bond, it's no matter. Just a bond and a lone pair. Bonds and lone pairs are the repulsive units. Now we are considering around the central atom, right? So no lone pairs, only 2 bonds are there. 1, 2, 2 repulsive units. So 2 repulsive units means what is the shape? Linear. I'll show it to you all through the simulator. This is the simulator. I hope you all can see it. If not, let me know, okay? Right. This is the simulator. So now we have carbon, the central atom. We are going to add 2 bonds, double bonds. These are the 2 oxygens. So what is the shape now? What is the shape? Molecular geometry, linear. Molecular geometry means the shape, okay? Molecular geometry is linear. And the electron geometry is also linear because there are no lone pairs here now. The bond angle will be 180 degrees, okay? Yeah, 180 degrees. So that is the linear molecule. So that is, if you all are not having any lone pairs, it is easy to get, right? And then BF3. Also, now we are going to count the repulsive units. How many bonds are there? 3. Are there any lone pairs? No. So the number of repulsive units is 1, 2, 3. Right? So then you have boron, sorry, and then 3 bonds. 1, 2, 3. What's the shape? Trigonal plane. Electron geometry is also trigonal plane. And the bond angles will be 120. Right? So trigonal plane. Now you all are having PF3. So once you draw the Lewis structure, you will get a lone pair on phosphorus, right? So now how many repulsive units are on phosphorus? 1, 2, 3, 4. What are the repulsive units? Bond pairs and the lone pairs, right? So there are 4 repulsive units. Now we'll put the 4 repulsive units. Phosphorus and 4 repulsive units. 1, 2, 3, 4. Now, if we just put 4, because there are 4 repulsive units, what's the shape? Tetrahedral. What's the electron pair geometry? Tetrahedral, right? And the angle is 109.5. But for phosphorus, there is a lone pair, right? It has a lone pair. So when you have a lone pair, you remove them. Remove the lone pair from the tetrahedral shape. Just remove the lone pair and get it, right? So if you go for it, now from this, you're going to remove this one. You are going to make this one a lone pair. We'll see what happens. You remove one single bond and add a lone pair. Now what's the shape? Trigonal pyramidal, right? It was tetrahedral. Once you remove the lone pair, now in this simulator, we are adding a lone pair. We can't see the lone pair. Now, actually, we can see only the bonds, right? When we visualize it, we can see the bonds. We can't see the lone pair. So we have to remove a bond from tetrahedral. From the electron pair geometry, just remove a bond for one lone pair. Then you will get trigonal pyramidal shape. Okay. So this is the trigonal pyramidal shape and you can see the angles are still 109.5. Just the shape only changed for trigonal pyramidal. Electron geometry is still tetrahedral. Electron geometry is actual one with the lone pair. In the shape, when we are considering the molecular geometry, we have to neglect the, we have to remove the lone pair from the electron pair geometry. So once we do that, we get the trigonal pyramidal shape. Okay, did you all understand that? Please let me know. First of all, did you all understand how to get that shortcut? Okay, good. If you all didn't understand, let me know. I can explain it again, okay? Right, so PF3 is a, what is the shape? Trigonal pyramidal. This is a mistake here. This is a mistake. This should be trigonal pyramidal, okay? Trigonal pyramidal. Please note that the shape is trigonal pyramidal. Right. So what are the other molecules I have? CF4. CF4 is tetrahedral. I showed you all earlier. Now CF4 is having 4 repulsive units, right? So 1, 2, 3, and 4. Both the molecular shape and the electron pair geometry is tetrahedral. There are no lone pairs. So the number of repulsive units is 4, right? No lone pairs. So 1, 2, 3, 4 repulsive units. 4 repulsive units means tetrahedral shape. Okay. So when we come to HCF4, Now, how many repulsive units? Count the lone pairs and the bond pairs. 1, 2, 3, 4, 5, 6. 6 repulsive units. So, add 6 repulsive units. 1, 2, 3, 4, 5, 6. Right? Okay. Now, what's the shape? Octahedral. What's the electron pair geometry? Octahedral. See, all are perpendicular to each other. 90 degrees bond angle between every atom, between the bonds, I'm sorry. So the molecular shape will be octahedral and the electron pair geometry will be octahedral. But in our structure, there are 2 lone pairs. 2 lone pairs, if it comes as a repulsive unit, what did I say? What did I recommend to do? To remove the lone pairs from the structure. So what happens when you remove 2 lone pairs from the structure? Just remove 2 bonds and check. Remove 2 bonds and add 2 lone pairs, right? Okay. This is giving tetrahedral shape because it's a lone pair. Now we have to add 2 lone pairs. Okay. Now what is the shape? Square planar, right? This is the square plane. Okay, I hope you can see it now. This is the square plane and the electron pair geometry is octahedral. From the electron pair geometry, what did we do? We remove the 2 lone pairs. Then what we get is a square planar molecule. Okay, so this way, if you all practice with the help of a simulator like this, you will save time during the paper, or else you'll have to go from first and divide the repulsive units by the number of electrons, count the electrons, and get the shape of the molecule, which is going to be a bit of a hard task. But if you practice it well, if you're okay with that totally, then it's totally fine. But if you're looking for new ways like to save time during the paper to do this bonding MCQs very fast, this is the easy method. Practice it with the simulator, you will get it. If you all didn't understand it now, okay, I can explain. Okay, I'll explain. Right. Okay, Shuhaila, I'll explain it to you from the PF3 molecule, okay? PF3 molecule. Now this has how many repulsive units? First, count the number of repulsive units. 1, 2, 3, and 4. What are repulsive units? The bonding pairs and the lone pairs. Any bond, if it is a single bond, double bond, or triple bond, it doesn't matter. Count the number of bonds, count the number of lone pairs. That is the number of repulsive units, right? So here, how many bonds? 3. How many lone pairs? 1. So there are 4 repulsive units, right? So when you have 4 repulsive units, generally what is the shape? Tetrahedral, right? 1, 2, 3, 4. What is the shape? Tetrahedral, right? But now, in our tetrahedral shape, if this lone pair was a bond, it is tetrahedral. Now it is a lone pair. No? So when a lone pair comes, the shape is changing. The tetrahedral electron pair geometry is changing if there's a lone pair because of the repulsions, okay? So when a lone pair comes, just from the tetrahedral structure, just remove one bond from the tetrahedral structure. Okay, when you remove one bond and add a lone pair instead, you will get the trigonal pyramid. Okay. Now here, just think that this is a lone pair. This vertical bond is a lone pair. Now think if that vertical bond is not there, then what is the shape? It's trigonal pyramidal, right? So just remove one bond, then you will get the trigonal pyramidal shape, right? Did you get it now? Did you understand it now, Shuhaila? Okay, good. Okay, Akila, can you show the other way of finding the shape? The other way means you need the traditional way. You mean this way? Okay, no worries. Akila? All right, okay. Okay, so the traditional way is, now if it is carbon dioxide, the traditional way is mentioned in your A-level resource book. Please go through with the resource book, okay? From the resource book, you can get the theory to do it very clearly. Okay, this is the shortcut I told you all to save time. Right. So the traditional way is you take carbon. How many electrons are given to the bond from the carbon atom? 1, 2, 3, 4. So 4. Then electrons from 2 oxygen atoms. One oxygen atom gives 1, 2 electrons. This one gives 1, 2 electrons. Then there are 2 oxygen atoms now multiplied by 2 equal to 4. So the total number of electrons in these 2 bonds is 8, right? So 8 divided by the number of repulsive units is 4, right? And if there are 4, now there are 1. Okay. Oh, sorry, I have done a mistake here. Right, sorry, my bad, okay. Yeah, the number of repulsive units are 2. Okay, so you divide 8 by 2 and get 4, and then you distribute the double bonds, right? These single bonds will become double bonds because of this 8 divided by 2, 4. And then lone pairs on the carbon atom is 0 now. So the shape will be linear, not tetrahedral, linear. Did you get it? I'm sorry, I have done a mistake, yeah? Okay, right. Okay, then the SF6 molecule, it has 6 repulsive units. 6 bonds means 6 repulsive units now. Right. 6 bonds means 6 repulsive units. So then what's the shape? Octahedral. I think I don't have to draw it again. Okay. 1, 2, 3, 4, 5, 6. Right? 6 repulsive units means shape is octahedral. No lone pairs. Okay. Right. So the second one is true. All the molecules have different shapes. This is linear, this is trigonal pyramidal, this is linear, this is trigonal planar, this is trigonal pyramidal, this is tetrahedral, square planar, and octahedral. Okay, did you all get how to find the shapes? Is there anyone still having doubts? If so, I'll answer at the end of the session. Okay, put your doubts specifically and right. Good, thank you. Right. Third one is all the molecules do not obey the octet rule. Right. Now, what is octet rule? Octet rule means filling up to 8. 8 means octet. Octet means 8. Okay. So for second period elements, the valence shell can fill up to 8 electrons maximum. Okay. 8 electrons maximum for second period elements. For third period elements, up to 18 electrons is permitted. It can be filled, no problem. But 8 electrons is the octet. Octet is complete for third period elements, but it can go up to 18 electrons, right? So in these molecules, now we have to find after bonding. Now the main purpose of bonding is to complete the octet and achieve the stability. Now. So now that's what we are going to find out, whether the octet has been achieved by these molecules. So the first molecule is carbon dioxide. After carbon bonds with oxygen, has the octet of carbon and has the octet of oxygen be completed. Now, how to find that? Now, carbon is giving 4 electrons to the bond. 1, 2, 3, and 4. And oxygen is giving another. Oxygen is giving 2. 1, 2. So 1. Then for carbon atom, after bonding with oxygen, how many total electrons will be there? Count like this. In this one, 2, right? 1, 2, 3, 4, 5, 6, 7, 8. Then has the octet of carbon completed? Yes, right? 8 electrons in its valence shell. So after it gets bonded with oxygens, the octet of carbon will be completed. Now we'll consider oxygen. If oxygen is there, it's giving 2 electrons to the bond. And it has 1, 2, 3, 4 electrons as lone pairs, as lone electrons, right? So now we'll count how many electrons in its valence shell. 1, 2, 3, 4, 5, 6, 7, 8. Now is the octet completed? Yes, right? So this carbon dioxide molecule has completed octet. Did you all get that? If you didn't understand, let me know. Okay. And boron. Now when we come to boron, count the number of electrons that boron has after bonding. 1, 2, 3, 4, 5, 6. Only 6 electrons. But boron is a second period element. That means 8 electrons maximum it can go. And 8 electrons is the octet, right? So 6 electrons only it's having after bonding. That means its octet is incomplete. When we consider fluorine, 1, 2, 3, 4, 5, 6, 7, 8. Fluorine has completed the octet. But boron has not completed the octet. So this molecule is having an incomplete octet, right? Okay. So in PF3 it's the same thing. How to count the octet? 1, 2. Count the lone pair separately as 1, 2. Lone electron separately. 1, 2. Bonds counted double. Why? Because fluorine is also given 1 and phosphorus 1 is also here. So 1, 2, 3, 4, 5, 6, 7, 8. Octet is complete. If you count for fluorine, octet is complete. So that is an octet complete molecule. But phosphorus is a third period element. So 8 up to 18 electrons is permitted for it in its valence shell. But here 8 has formed. So octet is complete, right? Carbon 1, 2, 3, 4. We have to count the octet, right? Okay. 1, 2, 3, 4, 5, 6, 7, 8. Octet is complete. For fluorine also octet is complete. That means this molecule has completed octet, right? Then next one, HCF4. Count the number of electrons after it has formed the covalent bonds, right? 1, 2, 3, 4. Sorry, I'm sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 electrons are there. 12 electrons are there means for xenon it's permitted, but the octet is exceeded, right? Octet means 8 electrons. No? So it is not, octet is complete, but it is exceeded. And 12 electrons is permitted. So the structure is stable, but the octet has got exceeded. So it is not the octet anymore. Okay. SF6, let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, the same thing. 12 electrons are there around sulfur after it is bonding with 6 of fluorine. So then the octet will be exceeded. So the third statement, all the molecules do not obey the octet rule. That is a correct statement. Do not obey the octet rule. Right. Fourth one, all molecules are nonpolar. Okay. Nonpolar means the dipole moment of the molecule should be 0. That is the theory, okay? You have to remember just the theory, just the point to do the MCQ. Go from the basics. Okay. So nonpolar means the dipole moment of the molecule is 0. For the dipole moment to be 0, the shapes of the molecule should be linear, trigonal planar, tetrahedral, square planar, octahedral. These are the shapes. In these shapes, if it comes, the molecule is nonpolar. By main reason is dipole moment is 0. The only reason is dipole moment is 0. So if you have to check whether a molecule is polar or nonpolar, check whether dipole moment is 0. If it is 0, nonpolar, right? Now in a linear molecule, now carbon dioxide is a linear molecule, right? So when we consider the dipole moment of the molecule, first we have to consider the dipole moment of individual bonds, right? So carbon is delta plus, as I showed you all earlier. Oxygen is delta minus. So the dipole moment will be from carbon to oxygen towards the most electronegative atom. Then when we consider this side bond, the left-hand side bond of carbon-oxygen also, the dipole moment will be towards oxygen. So when these two dipole moments are there in the opposite direction and in the same magnitude, the dipole moment will be of the molecule will be 0. So in all linear molecules, this is the case. That's why in linear molecules, dipole moment is 0. Did you all get that? Why the dipole moment is 0? Okay, because it is cancelling off. We have to take the dipole moments of the individual bonds and then check the dipole moment of the entire molecule. These two are getting cancelled off. That's why the dipole moment of the molecule is 0. Okay, same when it is trigonal plane. Now, the BF3 is trigonal planar, right? So when we draw the dipole moment of these individual bonds, what is happening? One will be to this side, one will be to this side, always towards fluorine. Why? Because fluorine is mostly electronegative. Here it should be delta minus. It is a mistake, okay? Here it should be delta minus, right? Okay, boron is only delta plus. So the dipole moments will go like this, and this dipole moment and this dipole moment has a resultant dipole moment in this direction, downward direction. I think it's not very clear, but these two will have a resultant dipole moment in the downward direction. This is like vector quantities in physics, like that, okay? So these two dipole moments will have a resultant dipole moment in the downward direction. So this dipole moment will cancel off with this dipole moment. Then the dipole moment of this molecule will be 0. Okay, right. And then PF3. PF3, when we consider, it has a lone pair, right? It doesn't have a bond here. So when we consider the dipole moments always towards fluorine, why? Because dipole moment is going from the less electronegative atom to the more electronegative atom, or from the partial positive charge to the partial negative charge. Okay, so that is how it's going, the dipole moment. So when it's going like that, the dipole moment is not equal to 0. Why? Anywhere the resultants are not cancelled. These two resultant will be in this direction. Then that resultant and this one will be in another direction, right? So the total dipole moment will be in the downward direction. That means it is not equal to 0. This is a trigonal pyramidal shape, right? So trigonal pyramidal means it's a polar molecule. Trigonal pyramidal means no, dipole moment is not equal to 0. Not equal to 0 dipole moment means it is a polar molecule. Okay. And CF4 is tetrahedral molecule. I just showed you all. So, and in the same way, the dipole moments will be distributed, right? And the resultants will be cancelling off, that these two resultant will be in this direction. After that resultant and this resultant will be in this direction. So those two resultant is there, no, that resultant will get cancelled off with this resultant. Okay, I'll show it again. These two resultant in this direction. These two resultant in this direction. Then this resultant and this resultant will be in the downward direction. That resultant will get cancelled off with this dipole moment. Listen very carefully, okay? So when it gets cancelled, the dipole moment of the molecule will be 0. That's why it is a nonpolar molecule. If you all didn't understand, let me know. Okay, SF6 is again, dipole moment is 0. It is an octahedral molecule. XCF4 dipole moment is 0 because here this diagonal dipole moment will get cancelled off. Okay. CF4 can show it again. Okay. Dipole moment of this pair planar molecule will be 0, right? Because see, the diagonals dipole moment is cancelling off. Okay. CF4, what's the problem in that? Okay, this is CF4. Okay, I'll try to draw it. Now this dipole moment and this dipole moment resultant is this. Okay, then this dipole moment and this resultant one's dipole moment will be here. Okay, then when we consider this one and this one, their resultant will be here, right? So that one, this one will cancel off with this one. Got it? That's why it is nonpolar. Is trigonal bipyramidal nonpolar? Trigonal bipyramidal, yes, trigonal bipyramidal is also nonpolar. I have not mentioned. Okay, sorry. Trigonal bipyramidal is also nonpolar. The shape, okay? I have mentioned the shapes which are mostly coming in this question. Okay, Yusra, right? Okay, Akiva. Right. Okay. So then all the molecules are non-polar is a wrong statement. There were polar molecules, right? Because of their shape, there were polar molecules like PF3 is a polar molecule. Yeah, PF3 is the polar molecule here. Yeah, so PF3 is the polar molecule. So all the molecules are non-polar is a wrong statement. So what is the answer? Number 4. Only two molecules possess lone pairs of electrons on their central atoms. Now, which one had lone pairs? Okay, did carbon dioxide have lone pairs on carbon? Central atoms means carbon, right? Did carbon have lone pairs? No. Did boron have lone pairs? No. Okay. Right, did phosphorus have lone pairs? Yes. And again, carbon, no. Xenon, yes. And sulfur, no. So there were molecules with lone pairs. Those are the two, PF3 and HCF4. Okay, wait. PF3 and HCF4 are the molecules which are having lone pairs. So that is the correct statement. Now, what is about the third statement? Because it says all the molecules do not obey the octet. Yes, all the molecules do not obey the octet. BF3 is not obeying the octet. HCF6 is not obeying the octet. Right? So all the molecules do not obey the octet rule is a correct statement. They are asking us to find the wrong state. All the molecules do not obey the octet rule. But carbon dioxide and PF3 obeys the octet. Yeah, only carbon dioxide and PF3 is obeying the octet. No, they're asking about all the molecules. All the molecules do not obey the octet rule. Right? That is a correct statement. Do not obey the octet rule is the thing you have to highlight here. All the molecules do not obey the octet rule because of BF3, HCF4. They too do not obey the octet rule means. So then they are saying all the molecules do not obey. No. That is the correct statement. Did you get it? Shafaq. Okay, good. Right, so we'll move on to the next question. The oxidation state of nitrogen is -1 in. Right. Now this is actually a chemical calculation question. But I just put the answer here, so I'll tell it. Okay, so we have to find the oxidation state of nitrogen. Now let's take the oxidation state of nitrogen as as X. Okay, so there are 2 of nitrogen, 2 of X multiplied by oxidation state of oxygen is -2. I hope you all know that by now. If not, please refer to the resource book. Okay, they are in detail. Oxygen's oxidation state is -2 in these compounds. Okay, so then -2, and there are 4 of oxygen, so multiplied by 4, right? So the total charge of the molecule, is there a charge? No, that means the charge is 0, right? So put equal to 0, and then 2x is equal to +8 when we take this to this side. So then x is equal to +4. Here it should be plus, okay? I'm sorry. Here it should be plus. Okay, right. These are what I wrote during the A level, so there may be mistakes, like a lot. So please bear with me. This is a plus here, okay? Right, so N2O. Again, now here in all the examples, we have taken the oxidation state of nitrogen as X, okay? So 2x -2. Only one oxygen, no, -2 equal to 0. Then this 2 goes this side and x is equal to +1. And in here, x is equal to -3. X means what? Oxidation state of nitrogen. In this, it is -1, NO2F +5. So what are they asking? -1 in which molecule? -1 is in NH2OH. That is the 5th answer. Okay, right. Then third question. Several shapes of molecules originate based on the trigonal bipyramidal electron pair geometry around the central atom. They are, right, trigonal bipyramidal, right. Trigonal bipyramidal means 5 repulsive units. Okay, so 5 repulsive units means we'll see how. 1, 2, 3, 4, 5. Right, this is the trigonal bipyramidal shape. 5 repulsive units. Now, what are the structures which is originating from this trigonal bipyramidal shape? How are structures originating? If the from a particular shape or the electron pair geometry, other shapes are originating due to the presence of what? Lone pairs, right? So we'll put one lone pair, two lone pairs, three lone pairs, and see what is the shape that we are getting for this trigonal bipyramidal. For this, now if we remove, if we remove a bond and we put one lone pair, what is the shape? Seesaw shape. Do you all see the seesaw shape? Yeah, it's like this. This is the seesaw. Okay. Right, that's the seesaw shape. Seesaw shape, electron pair geometry is trigonal bipyramidal. Right. So that is if there is how many lone pairs? One lone pair. Here the seesaw shape, this is one lone pair. Now if there are two lone pairs, what will happen to the shape? It will be a, I'm sorry, again there are 1, 2, 3, 4, 5 and two lone pairs. Now what is the shape? Wait. It should be a T shape because if you remove two bonds, sorry. Yeah, see, so two lone pairs, it will be a T shape. Electron geometry is trigonal bipyramidal. Why? Because 5 repulsive units are there. 1, 2, 3, 4, 5 repulsive units means trigonal bipyramidal. From that, if two lone pairs are removed from the trigonal bipyramidal shape, you will get the T-shaped molecule. Two lone pairs means T-shape, right? The next one is if there are three lone pairs, right? Three lone pairs. Now what is the shape? Linear. Electron pair geometry is trigonal bipyramidal. 5 repulsive units are there now. So electron geometry won't change, trigonal bipyramidal. But because of these three lone pairs, the repulsions have caused the molecule to form a linear shape. So this linear shape is originating from the trigonal bipyramidal electron pair geometry. Okay. So what are the shapes which are originating? If there is one lone pair, now we saw it is a seesaw shape. Two lone pairs means T shape. Three lone pairs means linear shape, right? So the answer is what? Linear T-shape seesaw. Answer number 2. Did you all understand that? How to get the shapes again? Did you all get it? Okay. Right. The 5th question is, oh no, sorry. The 4th question is, which of the following is true with regard to the oxygen, oxygen angle of the nitrogen species? Right. Right. Now for this, you have to draw the Lewis structure. If you all need to draw the Lewis structure according to the traditional method, if you all were taught that way from the beginning, and you all have practiced it and you're very fluent with the timing and all, then you all can totally go with it. Just ignore this explanation, right? If you all need to save time and you need to learn the shortcut, please listen to it very carefully and draft the text, okay? So this is the shortcut to draw the Lewis structure. First, you draw the skeleton, oxygen, nitrogen, oxygen. Then distribute the valence electrons around each atom. For oxygen, normally how many valence electrons are there around the oxygen atom? 6. Nitrogen, 5. So when we consider nitrogen, 1, 2. Now there are double. For oxygen, first we'll put the 6. 1, 2, 3, 4, 5, 6. For this oxygen also 1, 2, 3, 4, 5, 6. These 2 electrons are given to the bond. These 2 electrons are given to the bond. Then for nitrogen, now how many electrons are given to the bond? 1, 2, 3, 4. 4 electrons are only given, right? But now see, 5 electrons are there. 1 electron is missing for nitrogen. Now check the octet completion after bonding for each atom. I taught you all how to check the octet completion. Count the electrons for each atom, whether it is 8. Oxygen, see 1, 2, 3, 4, 5, 6, 7, 8. Octet completed. For nitrogen, see 1, 2, 3, 4, 5, sorry, 1, 2, 3, 4, 5, 6, 7, 8. 8 is completed, right? So that means octet is completed. Now octet is also completed and nitrogen has, but still nitrogen has only 4 electrons. Now after octet is complete, can we add a lone electron to nitrogen? No, because octet is complete. Any more electrons can't come. So nitrogen will be having a plus charge because 1 electron is less, therefore positive charge. Therefore, the Lewis structure of NO2 plus is this, right? Did you all get the shortcut of how to draw Lewis structures? Did you all understand that? This is the Lewis structure and it has a linear shape. The bond angle is 180. Did you all understand the Lewis structure? If this is, okay, good. Right, now this, that is in NO2 plus, right? So in same way, we have to draw the Lewis structures for the other molecules which they have given in this type of question. Now you just can't find from this, no, just by looking at it. So you just have to draw the Lewis structures for each and every molecule, then try to compare the angle at once. Just don't look at the question and get stuck. You can see, there are different molecules. So just draw the Lewis structures for all the molecules, then find the angle, right? So this molecule, it is a bent shape. Why is it bent? How many repulsive units? 3. So when there are 3 repulsive units, out of them 1 is a lone pair, means 1, 2, and 1 is a lone pair. What is the shape? Bent shape. Bent or angular or V shape. The electron pair geometry is what? Trigonal planar. 3 repulsive units, no? See, from the trigonal planar, 1, 2, 3. If you remove one bond from the trigonal planar, what is the shape you are getting? If you remove this vertical bond, what is the shape? Angular, bent, right? So that is what we are doing by adding a lone pair. It will become angular. Okay. Okay, Yusra, which one to explain it again? Put the question number, I'll explain it at the end. Okay. You are meaning the Lewis structures. Okay, I'll explain it at the end. If you all already know a method to draw the Lewis structure, which is a traditional method, it's okay, no problem, draw it that way, okay? If you all really need to save time and do it, this is, I can recommend this way, okay? Okay. Great. So then you do that for all the molecules. For this molecule, the shape is bent. Bent means, is the angle 180? No, right? It is less than 180. This angle is also less than 180. This is a tetrahedral molecule, no lone pairs. Then what is the bond angle? 109.5, right? So from that itself, we can tell that this is having the greatest bond angle. The less bond angle, and this is 180. No, so it is having the greatest bond angle, right? So it should be this way. So what are the answers which you can cut? You can use the method of elimination here. That means you're seeing the answers and eliminating it out of the answers. If it is not, you're eliminating, it is not correct. Okay. NO2 plus, NO43 minus. Okay, so you can tell fifth one is wrong, second one is wrong, fourth one is wrong. So out of the first and the third, now you have to compare just these two, NO2, NO2 minus, which one is having the greater bond angle. So NO2 is this, NO2 minus, NO2 is this, NO2 minus is this, right? Now if we compare the shapes, the shapes will be the same, right? Bent. But NO2 minus has one lone pair. Here it's not visible, it's one lone pair on the nitrogen. Therefore, the repulsion on the bond pair is high. This lone pair is, there are 2 electrons, no? So that will, that will have a higher repulsion on the bonding, bond pair, higher repulsion. That means the bond pair will come closer and closer. So this bond angle will be lesser, much lesser than 120, right? This NO2 has 1 electron on nitrogen. So the repulsion on the bond pair is lesser than this one. So the bond pair will come close, but not as close as this one. So it is just lesser than 120, not much less, just lesser. Okay, so which is having the greater bond angle? This one, NO2. NO2 minus is having a lesser bond angle than NO2. Because of it has a lone pair, this has only one lone electron. So what is the answer? Answer number 3. Right. Fifth one, which of the following statements are correct with regards to NH3 and NF3? Now, these two are very important molecules when it comes to the A-level paper. Always they ask about NH3, NF3, compare their properties of those two molecules. What are the differences between those two molecules? So I recommend you to have like a short note on NH3 and NF3. It will be useful, okay? So the first one is bonded pair repulsions are weaker in NF3 than in NH3. Okay, now first we'll come to the molecules NH3 and NF3. These are the two molecules. Okay. Now here nitrogen is more electronegative than hydrogen. So the partial negative charge will be on nitrogen. This bond the electrons in this bond will be spending more time closer towards nitrogen than hydrogen. Right? So if more electrons are gathering near nitrogen, it is gaining a partial negative charge. Then the hydrogen, the electrons are moving away from hydrogen. So it will have less electrons around hydrogen, less negative charges. Less negative charges means what is the partial charge here? Positive. That is the way. Okay. Why is that happening? Because nitrogen is more electronegative than hydrogen. Right. And when we come to nitrogen and fluorine, now fluorine is more electronegative than nitrogen. Fluorine is the most electronegative element. So fluorine is more electronegative than nitrogen. That means the electrons of this bond will be spending more time closer to fluorine. That means more negative charges around fluorine. So partial negative charges on fluorine and partial positive charges on nitrogen, right? So now these electrons will be spending more time closer to nitrogen in NH3. That means what? Electrons, so many electrons here, so many electrons here, so many electrons here. So this electron will be repulsion, repelling each other. That means this bond pair, this bond pair, this bond pair to bond pair repulsions will be high. Bond pair repulsions. In here, where are the electrons spending more time? Towards fluorine. So near nitrogen, near the bonds. Now here we take the bond angle. Near the bonds, are there electrons? No, much less. Much less electrons near the nitrogen. Therefore, are there greater repulsions or lesser repulsions? Lesser repulsions, because electrons are spending more time here, further away from the central atom. Right? So here there are less electrons, therefore less repulsion. Bond pair repulsion is less. Right? So the first statement or the A statement is correct. Right. And NF3 has a higher dipole moment than NH3. NH3, which is having the higher dipole moment. Now here, the lone pair moment is affecting the dipole moment. Okay, here the lone pair moment is in the same direction as the dipole moment. This is the dipole moment, this is a lone pair. These two are in the same direction means resultant moment is in the same direction, right? I'm sorry, the dipole moment is in the same direction. So this is having a greater dipole moment. In this, lone pair moment is up, resultant moment is down. That means what is happening? The dipole moment of this molecule will be lesser, right? So the B statement is wrong. And then NF3 is a stronger Lewis base than NH3. What is a Lewis base? Donating or accepting electrons. That is the main theory here. Lewis base means donating the electrons, right? Donating the electrons means base, Lewis base. So electron density in NH3, the electron density on nitrogen is higher. So when the electron density on that atom is higher, it can give out more electrons. It is easy to give out electrons. Therefore, it is the strong Lewis base than NH3. Therefore, the C statement is wrong. Okay. And the electronegativity difference, this is wrong. The electronegativity difference between nitrogen and hydrogen in ammonia and that between nitrogen and fluorine in NF3 are nearly equal. Now they are talking about the electronegativity difference. Now you don't have to know the values, but you can get them from their atomic sizes, right? Nitrogen is 3. Now I'll explain it from the values, but you can get it from the atomic sizes, okay? And also you all know that fluorine is anyways more electronegative than hydrogen. So this is the electronegativity difference. So when you get that, which is having the greater electronegativity difference? NF3, right? So the D statement is correct. No, sorry, I'm sorry. NF3, the NF bond electronegativity difference is 1. In NH3, NH bond electronegativity difference is 0.9. So there's a very close difference between these two. They are nearly equal, 0.9 and 1.0, nearly equal. So the D statement is correct. So what is the answer? A and D correct means answer number 4. Okay. Now I'm speeding up a bit. If you all don't understand, let me know. Okay. Give me a second. Okay, Akila, I'll let you know that. Sixth one. Akila, I'll be answering no one at last. Okay, fifth time. Sixth one. Which of the following statements regarding methyl benzene is correct? Are correct. All the carbon atoms lie in the same plane. This is methyl benzene. Now, how do we see whether it's lied in the same plane? From the hybridization, right? So this is sp2. Hybridization is coming for the shape. From the hybridization, we can determine the shape. From the shape, we can tell whether it's in the same plane or not. Okay. So each of these carbon in this molecule here is sp2, right? I hope you all know how to get that. And here it is sp3. So even though here it is sp3, here sp3 means tetrahedral. No? These hydrogen atoms are not in the same plane, but these carbon atoms are all in the same plane. These two carbons are also in the same plane. These ones are in different planes. Okay. So all the carbon atoms lie in the same plane. So correct state. Length of all carbon-carbon bonds are equal to each other. That is a wrong state. These carbon-carbon bonds are equal, but consider this bond and this bond. They too are not equal because of the hybridization, right? Different hybridization, different bond lengths. So these two bond lengths are not equal means this statement is wrong. Lengths of all carbon-hydrogen bonds are equal. Is that correct? That is again wrong because of the hybridization. This is sp3, this is sp2. So then their bond lengths are different. So that is also wrong. All carbon-hydrogen bonds means wrong. We have to consider this methyl part also. Any carbon-carbon-carbon bond angle is 120. See, any carbon-carbon, 1, 2. Now we know obviously these ones are having 120. So what we'll check is these three. These three will be having 120. Why? It is a trigonal planar. Right? Trigonal planar means bond angle is 120. So any carbon-carbon-carbon bond angle is 120. It's a correct statement. A and D correct means what's the answer? Answer number 4. Right? Then the last question of 2017. Carbon-oxygen bonds in bicarbonate ion are equal. How do we say that? From their resonance structures. If they ask about whether the bond lengths in a particular molecule are equal, then you have to consider their resonance structures, right? This is the structure of bicarbonate ion. This carbon, you have to consider resonance hybrid, okay? So when we draw the resonance hybrid, we use only the stable resonance structures. We don't consider this one, okay? We consider only the stable resonance structures and we draw the resonance hybrid. Then you can see this bond and this bond are having the same bond length, right? Because in the resonance hybrid, we will be writing the bond like this, and here the dot dot bond, right? So that these two bonds, I'm sorry. Okay, these two bonds will be having the same bond length. But consider this bond length is equal, but this bond and this one is not equal. This one and this one might be equal. But when we draw the resonance hybrid structure, this one and this one will not be equal, right? So all the carbon-oxygen bonds in this molecule are not identical. Why? Because of this bond. Okay, because of this bond, it is not identical. Right. Then we come to 2018 one. Okay, sorry. Bicarbonate ion is a resonance hybrid of 3 stable resonance structures. Is it 3 stable resonance structures? No, only 2 stable resonance structures. So that is also wrong. Both statements are wrong, means answer number 5. Okay. Then 2018 question number 8. The correct answer when the molecules oxygen, water, H2O2, OF2 and O2F2 are arranged in the decreasing order of the oxidation state of oxygen. Right, this is again about the oxidation state. Okay. Take X and find the oxidation state of oxygen. Hydrogen is always +1 with metals. I have given here. Right. So in water it is 2. In hydrogen peroxide it is -1. Oxidation state of 1 oxygen atom. Okay. And oxygen is PO, means the oxidation state of oxygen is 0. And here it is +2. Fluorine is always -1 in compounds. Why is that? Because fluorine is a strong oxidizing agent. Oxidizing agent means it will undergo reduction. -1 will become 0. Right? Then F2O2, it is +1 oxidation state. So when you arrange it in order, you will be getting the answer number 5. Okay. Right. The most acceptable Lewis structure for the thiocyanate ion is Cn- is what? We're asking the most acceptable Lewis structure. Right. So to draw acceptable Lewis structure, there are 3 rules. Okay. First rule is minimum formal charge separation. What is formal charge? Just a charge, plus and minus. If there is less plus and minus separation around the molecule, that means it is an acceptable Lewis structure. Not only that, octet completion for second period elements. Second period elements should definitely complete octet. 8 electrons should be there. Only few exceptions are there. They cannot come. Third period elements can exceed, no? So octet completion will already be there, no? So that is not a factor for third period elements, right? So higher electronegative atoms should get the negative charge. That is the next point for a Lewis structure to be accepted. So when we consider this one, it's the second answer. Why is that? Because see, minimum formal charge separation, only one charge is there. And most electronegative atom out of these 3 is what? Nitrogen. We can tell from the atomic radius. Okay, when atomic radius decreases, electronegativity increases. That is in the first lesson. So then the electronegativity of nitrogen. Yes, I will give the answers PDF in the group. Okay. So the electronegativity of nitrogen is higher. And the highest electronegative atom is getting the negative charge. So it is the most stable molecule. Now consider the first one. Sulfur is getting a negative charge. Sulfur getting the negative charge means it's wrong, right? Because nitrogen is the most electronegative. Now here we said most electronegative atom should get the negative charge. So that is wrong. Third one is wrong. Why? Because high formal charge separation. If we can draw the structure with minimal formal charge separation, then why should we draw the structure with higher charge separation? Not required, right? So this is a wrong structure. Not wrong, I mean not acceptable. And then here minus has come on carbon. That is also again not acceptable because of this reason. Nitrogen is only more electronegative. So the charge should be, negative charge should be a nitrogen. Again, fifth one, there is a greater formal charge separation. So that is not the answer. So ninth one, answer number 2. Right? And the 10th question, the increase in order of the boiling points. Okay, now boiling points in this bonding lesson is again very important. Yes, first one is wrong. Wrong means it is not acceptable, okay? Akila. Right. The increase in order of the boiling points. Boiling point is very important when it comes to bonding. Listen carefully and learn the theory properly. Go from the basic, then you won't get wrong, okay? So boiling points and melting points depends on 3 factors. Okay, first one is strength of intermolecular interactions. If there are compounds and if the intermolecular interactions are equal, then we have to consider their molecular weight to compare the boiling points. If the molecular weights are also equal, then we have to consider the surface area. So intermolecular interactions, mainly there is hydrogen bonds, dipole-dipole interactions, and London forces, right? In the given, what is the given ones? In this, all are non-polar molecules, right? Non-polar molecules. So everything will be having London forces. That is the intermolecular interactions in all these molecules, right? So all will be having what type of forces? London forces. Therefore, can we compare their boiling points using the intermolecular weight? Intermolecular interactions? No. So then what is the next factor? Molecular weight. Okay. Next, we have to compare the molecular weights. So when we compare the molecular weights, we can tell from the atomic sizes. Okay. No need to know the exact to the point molecular weight of each and every molecule. Can compare from the atomic sizes, right? So molecular weights, now I have marked here. According to this order, molecular weight is increasing. When molecular weight is increasing, in that, now if there is a CBr4 solution and a CCl4 solution, CBr4 molecular weight is higher now. So that means it is difficult to break the CBr4 structure. Okay. So if it is difficult to break the structure, their boiling point will be high. We have to give more heat in order to break, right? So that's why the boiling point is high. Boiling point is the heat which we should give to break the molecule and go to the vapor phase. Break the intermolecular interactions and go to the vapor phase. So in CBr4, higher molecular weight. Higher molecular weight means it is very difficult to break the intermolecular interactions, the London forces there. So we need a greater boiling point for it, right? So when the molecular weight is increasing, boiling point is increasing. So it will be in this order, right? So now according to that order, what is the answer? He and CBr4. This will be the answer, right? Answer number 3. Am I right? Is it answer number 3? Okay. 3 interactions to determine the type of interactions have for a molecule. Okay. Okay, now about the interactions, it is very clearly mentioned in the resource book. Detailedly, it is mentioned in the resource book. Now you want me to explain how to find the interactions, right? So yeah, it is clearly explained in the resource book. I just told you all about the shortcut. How to, not the shortcut, actually, the theory to find for determining melting points and boiling points. Go from these 3 factors. It will never get wrong. Okay. Then, right, hydrogen bonds means between hydrogen and a more electronegative atom, the bond is formed in a solution. In a solution or in a compound between hydrogen and a more electronegative atom, the bond is formed. That is only hydrogen bond. If there is hydrogen and a more electronegative atom, like nitrogen, oxygen, or fluorine, their hydrogen bond will be formed. Dipole is there in polar molecules. If there are polar molecules like ammonia and if there's ammonia, then that is a dipole interaction, because ammonia has a dipole, no? Delta plus, delta minus. So that delta plus of one ammonia will get attracted to the delta minus of the other ammonia, right? So there will be dipole interaction. And London forces are there in all the molecules. London forces are there in all polar and nonpolar molecules. Is it okay? The one who asked the question? Okay, good, thank you. And then, which of the following statements are true regarding the molecule given below? Right. So when a question like this is given, go one by one. Okay, don't try to do elimination method, anything here. Go one by one. For this earlier question, you all can use the elimination method, okay? For this question, you all can use the elimination method. For this one by one, okay? Just know the techniques, how to go. If there is a comparison, use elimination. If there is a ABCD statement, go one by one. Like that, just try to grasp the techniques, okay? Right. Which of the following statements are true regarding the molecule given below? All 4 carbon atoms lie in the same plane. So we'll consider the structure. Right. This is the structure. This carbon atom is sp3. This is sp. I think you all know how to determine the hybridization. Okay, I'll tell a shortcut. It's okay if you all didn't understand. Go with the traditional method. Okay, but try to understand. Give the full attention. To find the hybridization, just start from 1 and go like this. S 1 2 3. So sp3. S p p p. sp3. This one is S and P. If there is a triple bond, we consider only the sigma bonds. Okay, we have to consider only the sigma bonds and the lone pairs for the hybridization. Note that down if you all need. for hybridization shortcut, we have to consider only the sigma bonds and the lone pairs. Okay, right. So I think you all know what is a sigma bond. Okay? If there is a triple bond, one sigma bond, two pi bonds, likewise. So this carbon has one s, p, p, p. So sp3. If we consider carbon B, sp. So sp is the hybridization. We consider only the sigma bonds. Okay. So this carbon similarly sp. This carbon spp, sp2. Right. That is the hybridization. So all these 4 carbon atoms, as you can see, it lies in the same plane. So the first statement is correct. The angle between CDH and CDC. CDH, H is hydrogen, and CDC is 120. Yes. Why is that? Because this is having how many repulsive units? 3. You all can take this from the number of repulsive units and then go to the shape, or else hybridization and then go to the shape. Okay, any way you all prefer. So now if we consider the repulsive units and find the shape, trigonal planar means bond angle 120. And if we consider hybridization and find the shape, hybridization is sp2. sp2 means shape is trigonal planar means bond angle is 120. Right? So the second statement is a correct statement. Between CB and CC, 2 sigma bond, 1 pi bond. CB, CC. Can there be 2 sigma bonds in a molecule? No, always there's only 1 sigma bond. 2 pi bonds can be there. Any amount of pi bonds can be there. But 1 sigma bond only can be there. So that C statement is wrong. Between CB and CC, there is 1 sigma bonds and 2 pi bonds. That is correct. Okay, as I explained. So A correct, B correct, D correct means answer number 5. Right. So the next question. The lone pair of electrons on nitrogen in an amine has a lower tendency to form a bond with H plus than the lone pair of electrons on oxygen in an alcohol. By now, you all should know what does this mean. What does this mean? Lone pair of electrons is forming a bond with H plus. That means what? It is a Lewis acid or base. Lone pair of electrons is being donated to form a bond with H plus. So that means it is a Lewis base. Now they're asking which is better of a Lewis base, amine or alcohol, right? If you all didn't get that, I'll explain it again. The question is like this. They are saying lone pairs of electrons are going to get donated to form a bond with a H plus. Now lone pair of electrons donating means what is that compound? It is a Lewis base. So now they are saying which is a better Lewis base, amine or oxygen. And what is the reason for it? It is given in the next box, okay? So Lewis base means it should have the ability to donate. Base means donate. Acid means accept. Acid accept. AA. So you all can remember, right? Lewis base is only donating the electrons to form a bond with H plus. Okay. So now the strength of a Lewis base depends on 2 things. Electron density on the donor atom. Like earlier we saw for ammonia and NF3, like that. Electron density of the donor atom and the electronegativity of the donor atom. So clearly remember this theory, okay? Strength of a Lewis base is depending on 2 factors, 4 from the bases. What is the 2 factors? Electron density on the central atom and their electronegativity. Not central atom, the donor atom, okay? Right. So those 2 factors, if we consider for amine and for alcohol, which is a better Lewis base. For amine, electron density is there, right? Nitrogen is more electronegative. For oxygen also, like same the electron density, because oxygen is more electronegative. The electrons of this bond and this bond will be spending more time closer towards nitrogen and oxygen. So nitrogen and oxygen will be having almost the same electron density. So we can't compare the strength of the Lewis base depending on the electron density in this case. Because why? Nitrogen and oxygen both are electronegative atoms, right? Both are more electronegative atoms. Right. So now we have to compare the electronegativity of the donor atoms. So if we compare the electronegativity of nitrogen and the electronegativity of oxygen, which is greater, now wait, before that, the R groups, these are the R groups. CH3 is the R group of amine. CH3, CH2 is the R group of this alcohol, right? So the R groups are pushing the electrons. That it is called as induction. Okay. This is having a tendency to push the electrons towards the nitrogen. This is having a tendency to push the electrons towards oxygen. Therefore, anyways, the electron density of these two molecules are great, right? But oxygen is much more electronegative than nitrogen, right? That is a fact. I think you all know. Carbon, nitrogen, oxygen. Oxygen is having lower atomic radius than nitrogen. That means whose electronegativity is higher? Oxygen. So oxygen is more electronegative than nitrogen, right? Therefore, the electrons around oxygen is more attracted to oxygen than the electrons in the amines. In amines also it is attracted, but not as oxygen. Why? Because oxygen is more electronegative than nitrogen, right? Therefore, the ability to donate the electrons in this from this oxygen is less, because oxygen is greedily like keeping the electrons towards itself. It is all the electrons are attracted towards oxygen because it is more electronegative. So it will not like to donate the electrons, right? But amine is not like that. It can donate the electrons. Right. So did you all get that? Because oxygen is more electronegative, it will greedily keep the electrons. It will not donate easily. So the ability to donate is less. Therefore, the first statement is wrong. What is it saying? Amine is a better Lewis base than alcohol. So that is wrong. I'm sorry. They are saying amine has a lower tendency. So amine is a weaker Lewis base than alcohol. They are saying, but it is wrong. Amine is a stronger Lewis base than alcohol. Okay, so this statement is wrong. I hope you all got it. If not, let me know. Nitrogen is less electronegative than oxygen. That is anyways a wrong statement, no? Because of that atomic radius, as I explained. So, I'm sorry. Nitrogen is less electronegative than oxygen is a correct statement. So it is correct. First one wrong, second one correct means what is the answer? Answer number 4. Now what's the doubt? The R group pushers. Okay. So if there is a R group, there is a theory for this. Okay. If there is a R group, you all will learn it more, I think, in organic. If there is a R group attached to the central atom, the R group is more electron density. R group is a heavy group in this molecule. Here it is more heavy, right? So it will be keeping the push, it will keep pushing the electrons towards the electronegative atom. That is called induction. Okay. If you all don't understand induction, no need to worry about that. You all can just find out from the electronegativity of the atom, right? Because oxygen is more electronegative, it doesn't like to give out the electrons. Okay. Right, then the 13th question. Carbonate and sulfite ions have similar shapes. Central atoms of both have lone pairs of electrons. Okay, shapes and the lone pairs. Now this one is trigonal planar. 3 bonds, right? 3 bonds means trigonal planar. 1, 2, 3. 3 bonds, trigonal planar. And sulfite, if we consider, sulfite is having a lone pair. That means what is the, if we put a lone pair, see, electron geometry is tetrahedral. Shape is trigonal pyramidal. I explained this earlier, okay? So I'm not going to go into details now. 1 lone pair, therefore it is trigonal pyramidal. I think you can get the recording, just request the Majlis, okay? Right. So then carbonate and sulfate have similar shapes is a wrong statement. Central atoms of both have lone pairs is also again a wrong statement. So if both are wrong, what is going to be the answer? Answer number 5. Okay. See how simple it is when you like know the theory. If you know the theory and go from the basic to the point, it's very easy. You can finish the bonding MCQs within 30 seconds. One bonding MCQ, 30 seconds. Okay. The last question of 2018, the boiling point of this is higher than the boiling point of this aldehyde and this ketone. The carbon-oxygen double bond is stronger than the carbon-oxygen single bond. Okay, we have to compare now boiling point, melting point. So first we'll see the interactions. These molecules are all polar molecules. So they will have different types of interactions, right? So here it's hydrogen bonding. Why? Because oxygen, these are the same molecules within this solution. these two molecules will be having hydrogen bonding. All these molecules will be attracted to each other by hydrogen bonding, oxygen and hydrogen. More electronegative atom and hydrogen means that bonding is called hydrogen bonding. And in the aldehyde has a dipole-dipole interaction. It is not hydrogen. No hydrogens here not to bond. It can form a hydrogen bond from this one also. But apart from that, dipole-dipole is the prominent. Okay. So when you consider dipole-dipole, oxygen is more electronegative, so it has the negative pole. Carbon is less electronegative, so it has the positive pole. So when two molecules come together, the negative pole will be attracted to the positive pole. Positive pole will be attracted to the negative pole. This is the dipole-dipole interaction. Right. And then the next one is the ketone. Ketone is also again dipole-dipole interaction. So what is the first statement? Now we have to find the prominence. Which one is having greater, the strongest interactions? Hydrogen bonding is more stronger than dipole-dipole interactions. Therefore, this statement is correct. Okay, here hydrogen bonding, no, in this both dipole-dipole interactions. So obviously the boiling point is going to be greater. Okay, so this is correct. The carbon-oxygen double bond is stronger than the carbon-oxygen single bond. Okay, now we'll have to see about the bond strength. Bond strength means check the hybridization. Double bond means double bond or triple bond. Double bond means sp2 hybridization. Triple bond means sp hybridization. Single bond means sp3 hybridization, right? So when the S character is increasing, the electron density in the overlapping region. Now here see this is sp, sp. This is sp3, sp3. When sp, sp, the bigger orbitals, no. So the electron density in this overlapping region is greater. sp3, sp3 means longer orbitals. So the electron density in these two orbitals overlapping region will be less, right? So when the electron density in the overlapping region is greater, it is difficult to break that bond, right? So if it is difficult to break, that means that bond is strong. Okay, that is why double bonds are stronger than the single bonds. This is a correct statement, but does this explain this one? No, this boiling point is because of the intermolecule interactions, not because of the bond strength, right? So these two are correct, but this is not explained in the first statement. So the answer will be what? Answer number 2. Okay. So we'll go to this is answer number 2. Okay. 2019. The number of stable resonance structures that can be drawn for the oxalate ion. Okay, now resonance structures, I recommend you all to do as the last question of the paper, because you all have to draw all the resonance structures and check which one is stable, which one is unstable. If you all are having, if you all really need to go with the order, then you all can go ahead and do it, no problem. But I recommend you all to do this as the last question of the paper. Okay? Right, so we are having, these are the resonance structures of the oxalate ion. I hope you all know to draw the resonance structures. Just interchange the double bonds and interchange the charges. The entire process to draw the resonance structures, the step-by-step procedures given in the resource book, please refer to it, okay? The answer is answer number 3. Right. Then the 16th question. The electron pair geometry and the shape around the 2 nitrogen atoms. Okay. Now nitrogen 1, nitrogen 2, I have drawn the lone pairs for your reference. So in nitrogen 1, how many Vesper units? 4 Vesper units. 4 repulsive units. Therefore, the electron pair geometry, EPG means electron pair geometry. What is the electron pair geometry for 4 units? Tetrahedral. So now if you remove one lone pair from tetrahedral, what is the shape? Trigonal pyramid. I showed you earlier, right? N2 is having 3 Vesper units. Therefore, the electron pair geometry is trigonal planar. If you remove one lone pair, what is the shape? Angular, right? So the answer is answer number 1. That is the shortcut, okay, to do the shapes of the molecules, right? The increase in order of the electronegativity of the sulfur atom in these molecules. For this, you all have to draw the Lewis structures of each molecule and then determine the electronegativity. So I have given a table. Okay. So to determine the electronegativity of a covalent molecule or a covalent ion, there are mainly three factors: hybridization, charge, and the oxidation. First factor is the hybridization you all have to consider. So for hybridization, you all can use a shortcut which I thought and get the hybridization of sulfur. Here S123 sp3. S123 sp3. I said count the sigma bonds and the lone pairs. Okay. S12 sp2. S12 sp2. S123 sp3. Higher the S character, higher the electronegativity. In which is the S character greater? Now these three are sp3. Sulfur dioxide and sulfur trioxide are sp2. Therefore, what is happening? These two will have greater electronegativity than the other three. Therefore, if you consider here, first one will be wrong. Second one will also be wrong. Here you can use method of what? Method of elimination. In these comparison ones, mainly you can use method of elimination. Okay. So then the charge, then the charge is the second factor. Why higher S, higher electronegative? It is a fact. Okay. Higher S, higher electronegative means higher the S character, the electronegativity is higher. That is a fact. Okay. It is there in the resource book. For further reference, you can use a resource book. There is a reason. If there's time, I'll explain it at the last. Okay. Okay. Charge. Next, compare the charges on these atoms. On the sulfur atom in all of this molecule, is there a charge? No, so it is 0. So that means you all can find the electronegativity of sulfur. You all can't compare using the charge. Now, anyways, you all have to compare only SCl2, SO3 minus, and SO4 minus. No, we have ruled out these two. So the next factor is oxidation number. So higher the positive charge or higher the positive oxidation number, higher will be the electronegativity. Because if the plus charge is more, that means it like to attract electrons more. So the electronegativity will be higher. Now, if we compare sulfur dioxide and sulfur trioxide, these two are having same hybridization. So if we compare their charge, which one is having the greater positive charge? Sulfur trioxide. So that means the electronegativity of sulfur in sulfur trioxide is greater than in sulfur dioxide, right? Therefore, we can rule out the third one. See how to use the method of elimination. Now we have to just go for the fourth one as the answer. Okay. Fourth one is the answer. Why isn't it the fifth one? Because we got SO4 2 minus and SO3 2 minus. We'll see SO4 2 minus and SO3 2 minus. Again, the charge. SO4 2 minus is having greater positive charge than SO3 2 minus. That is why we are ruling out the fifth one. Okay. So that is how the electronegativity of the atom is. What are the three theories? Hybridization, charge, oxidation. Right. So it's simple if you know the theory to the point. Okay. Then the 18th one. Right. Then the 18th one, the incorrect statement. Did I miss a question? Okay. The incorrect statement with regard to the oxoacids of chlorine. Oxoacids of chlorine, HOCl, HClO2, HClO3, and HClO4 is the shapes around chlorine. Right. So if there are the shapes, first we have to draw the structures, skeletal structures. Not the skeletal structures, actually the Lewis structures. Okay. So when we draw like this, now they're asking the shape around chlorine, not around oxygen, not around this oxygen, not around hydrogen. They're asking the shape around, but around chlorine. So around chlorine, now how many repulsive units? 1, 2, 3, 4 repulsive units. 4 repulsive units means what's the electron pair geometry? Tetrahedral. From tetrahedral, if you take out 2 lone pairs, what is the shape? Angular. See? 4 repulsive units, tetrahedral. 1, 2, 3, 4. Right, tetrahedral. From this, now if you take out 1 repulsive units, you're going to remove from here. If you take out 2 repulsive units, you're going to remove 1 from here, 1 from here. This one and this one. If you remove, what is the shape? Angular. Remove the lone pairs, get the shape. From tetrahedral, 2 lone pairs, if it goes, means the shape is angular. Aphia. Isn't the electronegativity of SO2 minus more than that of SO2 minus? I think that's a mistake there. Can you send me the question again, please? Okay, thank you. So the shapes, right? Okay, the shape around chlorine is what? Angular, as I showed. If there are two lone pairs in a tetrahedral one, it is angular, right? Then likewise, next one is what? They're asking the oxidation state. So we'll go with the flow. Oxidation state is what? In chlorine, it is +3. Oxygen is more electronegative than chlorine, right? So these electrons of the bond will be spending more time closer to oxygen than to chlorine. So in chlorine, there will be plus charges, partial positive charge. So that will add up to the oxidation number of chlorine. So here it will be +1, 1 electron gone, +2, another electron gone, +3, another electron gone. 1, 2, 3 electrons gone towards oxygen. Means around chlorine, it is having a +3 oxidation state. Like that only we are taking the oxidation states of chlorine. Okay. In HOCl, what is the oxidation state? +1. I haven't drawn the molecule, but HOCl, you can draw and get the oxidation state. It is +1. HOCl2, it is +3. Right? And then HOCl, it's HClO3. Okay. Around Cl, how many repulsive units? 1, 2, 3, 4 repulsive units. 4 repulsive units means shape is tetrahedral. From tetrahedral shape, if you take off this one lone pair, what is the shape? Trigonal pyramidal. So trigonal pyramidal, what is the oxidation state? 1 gone, another one gone, another one gone, another one gone, another one gone. So 1, 2, 3, 4, 5, +5 oxidation state. Okay. Do you all understand how to get the oxidation state? If you all didn't understand, let me. Okay, then the next molecule. What is our next molecule? HClO4. So HClO4, what is the, how many repulsive units? 4 repulsive units. 4 repulsive units means what is the shape? Tetrahedral. Tetrahedral means tetrahedral, and also now we find the oxidation state. It will be 7. 1, 2, 3, 4, 5, 6, 7. +7. Okay. Right. Then first statements are correct. First and second statements are correct. Next one, the acidic strength varies as follows. Acidic strength. When the oxidation state of chlorine increases, acidic strength is increasing. That is a fact. That is a theory. Okay, acidic strength is determined by the oxidation state of chlorine. If chlorine has a higher oxidation state, acidic strength is greater. Therefore, the third one is correct. Fourth one, all these oxoacids contain at least one double bond. That is a wrong statement. Why? Because HOCl has 2 single bonds, only no double bonds. So that is obviously it is a wrong statement. All these oxoacids contain at least one OH group. That is correct. Oxoacids, acids are definitely going to have OH groups. So that is a correct statement. So it's answer number 4. Right. Isn't the answer for the 17th question 5? Isn't the electronegativity of SO32 minus and SO42 minus? Okay. SO32 minus, SO42 minus. SO32 minus, SO42 minus. Okay, now see, who is it? Afia. SO32 minus hybridization is sp3. SO42 minus hybridization is also sp3. Charge 0, charge 0. So we can't compare the electronegativity of the sulfur atom in this one and this one using the hybridization or the charge, right? So what we have to see is the oxidation number. In SO32 minus, what is the oxidation number? +4. Oxidation state is +4. In SO42 minus, what is the oxidation state? +6. So higher the positive charge or higher the positive oxidation state, higher the electronegativity. Therefore, SO42 minus is having greater electronegativity than SO32 minus, the sulfate. Okay, did you get it now? Okay. Right. Then next question. Among the halogens, I2 is a solid, whereas bromine is a liquid. London forces become stronger with the increase in the molecular surface area. Okay. Right. Now the theory here, what is the theory? The strength of the London forces is the theory. Why? Because they're asking whether it is a solid or a liquid, right? Now, before that, the physical state of a compound, of a molecule, will depend on the intermolecular interactions, whether they are solid or whether they are liquid or gases. It will depend on the strength of the intermolecular interactions. How strong is the intermolecular interactions will determine the state of the molecule. So that is a theory there. To what state of the molecule, to see what state, we have to see what is the strength of the intermolecular interactions, right? So now the strength of London forces, now I2, Br2, both are non-polar. That means both are having London forces for sure, right? So when we consider the strength of London forces is depending on distance between molecules. It is inversely proportional to the distance between the molecules. If two molecules are there, if it is very far, one molecule is here, one molecule is here, then distance between molecules is what? High. Right? When distance between molecules is high, strength of the London forces will be low. Right? And it is directly proportional to the surface area of the molecules. When there's greater surface area, greater London forces. Molecular weight greater means greater strength of London forces. This is the theory there. Okay, remember this theory. If you remember this basic theory, go from the basics. It is very important. Okay? So strength of the London forces inversely proportional to this, directly proportional to these two. Now what are they asking? Right. Okay. Yeah, it's answer number 1. And now we normally know that I2 is a black purple color solid, right? Normally we know it is a solid. And Br2 is the only liquid halogen, right? So this is a correct statement. We know by fact. Then London forces become stronger with increase in the surface area. That is correct. No, surface area increase means it is directly proportional. So strength of London forces increase. So that is correct statement. Both are correct. Is this explained in this? Yes. Because of these London forces are stronger. Now I2 is having greater surface area and it is having greater atomic radius than bromine. So that means it is having greater surface area. Greater surface area means greater London forces. So when the London forces are becoming more stronger, it is becoming more to the solid side. That is why I2 is a solid and bromine is a liquid, right? So this statement explains this statement. Therefore, the answer is answer number 1. Question number 20. Solubility of 1 butanol in water is less than the solubility of methanol in water. 1 butanol and methanol. Solubility. Okay. Solubility means again we have to consider the intermolecular interactions only. Okay. So 1 butanol in water solubility and methanol in water solubility. All means what? It is having a OH group. OH groups means what? It will have hydrogen bonds with water. With each other also it will have. That means methanol hydrogen bonds will also be there. Methanol water hydrogen bonds is also possible. Butanol hydrogen bonds is also there. Butanol water interaction hydrogen bonds is also possible. Right? So if they are forming hydrogen bonds, that means they are both soluble, but they're asking which is more soluble. Alkyl groups are hydrophobic. What are alkyl groups? These groups, this CH3, this carbon part is only called the alkyl groups. This is the alkyl group of methanol. This whole thing is the alkyl group of butanol, 1 butanol, right? So alkyl groups are this. When alkyl groups are there, alkyl groups are, they don't like water. Hydrophobic. Phobic means don't like, right? So alkyl groups are hydrophobic, means they do not like water. So if there are greater heavy alkyl groups, that means water solubility is less. Therefore, it is answer number 1. And the solubility of alcohols in water decreases as the size of the non-polar alkyl group increases related to the polar OH group. Yeah, when this one's alkyl group size is increasing, when this molecule is becoming more and more heavy, the water solubility is less. So it is explaining the first statement. So the answer is again answer number 1. First point, instead of OH, we put water. First point, instead of OH, we put water means which one? In 20th question, instead of OH, we didn't put water. Okay. Okay, now methanol is there. No? In the methanol bottle, methanol is only there. So this is one methanol molecule that will be interacting with another methanol molecule by hydrogen bonds. Okay, because it is having oxygen, this oxygen in this methanol will be forming a hydrogen bond with the other methanol. Ah, okay, you got it. Okay, right. Then 2020. Ah, okay. The number of unstable Lewis dot dash structures that can be drawn for the peroxynitric acid molecule. This is the formula. So they have given us the formula. So we just have to draw the Lewis structures. I recommend you all keep this also for the last because you all have to draw all the resonance structures to find, oh no, they're saying unstable. This you can do. Unstable means you all have to deny all the conditions, all those three conditions, which I said that is going to be acceptable for a Lewis structure. You all have to deny all those three conditions in order to draw the unstable one. So how many of those can you all draw? Yeah, unstable means high electronegative atoms get the positive charge. And there should be a high formal charge separation. See, these two structures are unstable. Here, oxygen is getting plus. Here, both the oxygens are getting plus. Here, oxygen is plus, nitrogen is plus, high formal charge separation. So, both of these are unstable. So, there are two unstable structures which can be drawn. Answer number 2. Right, next one. Consider the following compounds. Now, the variations in the boiling points, and they have given us the molecular weight. So boiling points, I said first you have to check what is the theory, intermolecular interactions, right? So first we'll consider the intermolecular interactions of these compounds. A is having London. See, no polarity. It is an unpolar molecule. A is London. B is also having London. No polar groups, no polarity. So it is having London. C is polar. It is an aldehyde. So what is the bond? What is the interaction? Dipole interaction. These have it is also aldehyde, again dipole interactions. E is alcohol, so it is having what? Hydrogen bonding. So, and when you compare, right, when you compare A and B, both are having London interactions, but chain molecules. This is called a chain molecule. This is unchained. This is a branched. These are having branches. This A molecule is branched here. So branched molecules. Okay. Okay, we'll take a break of like 3 minutes because the Azan is going on. Okay, so in the 22nd question, what I was discussing is I said that now we are comparing A and B. Okay, we are going to compare A and B. Both are having London forces, but now both are having London forces means we can't compare their boiling points using the strength of intermolecular interactions, right? So we have to now molecular mass is also same in A and B. So we had to go for what? Surface area. So A is a chain structure, B is a branch structure. So usually the theory is chain molecules is having a higher surface area. Chain molecules, this is the surface area, greater surface area than the branch molecules, right? So greater surface area means the boiling point is greater. So the A boiling point is greater than B. So from that we can see where A's boiling point is greater than B. Here A greater than B, A greater than B. Here A equal to B. That can't happen, right? So this is a wrong one. Here A is less than B. So this is a 1. So we can eliminate number 3 and number 4. Here A greater than B. So that is correct. Then next, D and C both are having dipole-dipole interactions. Both are having dipole-dipole interactions, and now we have to compare their surface area, D and C. I said the chain is having greater surface area than the branched ones. So C should be having greater boiling point than D. So C and D here, it's equal boiling point. No, so that is wrong. C and D here is greater than D. Okay. Here also C is greater than D. Now we have just 2 and 5 only we have to compare. Then E is having hydrogen bond. Therefore, the greatest intermolecular interaction strength is there in E. So then the boiling point is greatest in E. We'll say that in this both, yeah, E is having the greatest boiling point. So then we have to compare D and B. D and B. D is having dipole-dipole interactions. B is having just London forces. Dipole-dipole interactions are stronger than London forces. Therefore, D is having greater boiling point than B. So this is wrong. Here D is, yeah, this is correct. This is wrong. Here D is having lesser boiling point than B. So this is wrong. So the answer is answer number 2. Okay, did you all get it? Okay. 23. D is dipole. Yeah, D is dipole because it is aldehyde now. How do we decide? Dipole means now I said because there is an electronegativity difference. I showed in the earlier one, you all can go through the PDF of the answers I will be sending. In that, one of the explanations, it is that there is a electronegativity difference. 2 poles are created, partial positive charge, partial negative charge, right? So then that is the dipole-dipole one. Dipole-dipole means 2 poles, positive pole, negative pole is created. That is only dipole. Did you get it, Akila? Right. The increase in order of covalent character in the chemical species. Covalent character. Now, what is the theory there? Covalent character. Electronegativity difference. Electronegativity difference is only purely determining the covalent character and the ionic character, right? So, if there are 2 atoms which is forming a compound, whether it is ionic or covalent, how do we determine? By the electronegativity difference of those 2 atoms. Now we'll see the compounds which is given to us. Potassium and fluorine, potassium fluoride. So we take the electronegativity of potassium as X, electronegativity of fluorine as Y. Electronegativity of potassium X, electronegativity of fluorine as Z, right? So we already know that fluorine is having a greater electronegativity than fluorine. Therefore, Y is greater than Z. The reason is greater electronegativity. Why fluorine is having greater electronegativity than fluorine? Because it's the atomic radius lesser in fluorine, so it is having a greater electronegativity. Y greater than Z. Did everyone understand why is Y greater than Z? Okay. So everyone understood, right? Why is Y greater than Z? Because fluorine is having a small atomic radius than chlorine. Okay. Right. Then Now we have to compare the electronegativity difference. Potassium fluoride in this side, potassium chloride in this side. Potassium, now fluorine is having greater electronegativity than potassium also, so it is Y minus X, Z minus X. Since Y is greater than Z, Y minus X is greater than Z minus X, right? So the electronegativity difference of potassium fluoride is greater than the electronegativity difference of potassium chloride. Therefore, because it is having greater electronegativity difference, ionic nature is more. Greater electronegativity difference, no. So it is trying to go away from each other. It is not trying to bond. So electronegativity difference is greater means ionic nature is greater. Covalent nature is less. Okay. Therefore, KF is more ionic than KCl. Then same thing if we compare sodium chloride and sodium sulfide. Which one is more electronegative, sulfur or chlorine? Chlorine, right? So A minus X is greater than B minus X. Therefore, sodium chloride is more ionic than sulfur. The point atomic radius is greater. In which one? Yeah. Atomic radius of fluorine is greater than the atomic, if it is lesser than the atomic radius of chlorine. That is why the electronegativity of fluorine is greater than the electronegativity of chlorine. This Y is the electronegativity. Y is the electronegativity. The reason this has happened is because atomic radius is lesser in fluorine. Okay. Right. So in potassium fluoride and sodium chloride, if we compare this potassium, this fluorine in this potassium and fluorine atoms are smaller than sodium and chlorine atoms. If atoms are smaller, electronegativity difference is greater. Therefore, the ionic nature is great, right? So the answer is answer number 3. Okay. Then the 24th question, which of the following are correct statements regarding the following molecule? Okay. Now they have given us the molecule. So we have to draw, once they give us the molecule, just draw the electron pair geometry of that molecule. Okay, to find if they are asking to find whether they are in the same plane, no hybridization, no anything, just draw the electron pair geometry of that molecule. Now in this molecule, they have given like this. So we draw the electron pair geometry of that. First one is atoms labeled P, Q, R, and S lie on a straight line. Now where's P? P is here, Q is here, R, S. This is tetrahedral, no? So this P and Q is in a straight line, but P, Q, R are not in a straight line, right? So the first one is wrong. Second one, Q, R, S, and T on a straight line. Q, R, S, and T on a straight line. Second one is correct. R, S, T, U, and B. R, S, T, U, and B. They are not in a straight line, but they are in the same plane, right? Because this is a trigonal plane, and we can get it from the repulsive units, or we can get it from the hybridization. sp2 hybridization, therefore trigonal planar, or 3 repulsive units, therefore trigonal planar, right? So because it's trigonal planar, this is all in the same plane. This is linear, so it is obviously the same. So that is also a correct statement. Then when B and C are correct, yeah, you have to check the D statement. Atoms labeled R, S, T, and U lie on a straight line. R, S, T, and U. Is it on a straight line? No, right? Because this is trigonal planar, this is having a bond angle also, 120 degrees. So obviously it is not on a straight line. So the D statement is wrong. Answer number 2. B and C correct means answer number 2. Okay. Okay, then we come to the 2021. Do we have time to do that? There are just 3 questions. Okay, I'll just explain it quickly. The shapes are given. Right, these are the molecules. We have to find the shapes of them. IF4 plus, IF4 minus, and IF5. Right, IF4 plus, just draw the Lewis structure. How many repulsive units? Find the electron pair geometry, trigonal bipyramidal. From that, remove 1 lone pair. Then seesaw shape. Like that, do the same for other 2 as well. Okay. Then you will get the answer as answer number 1. Okay. Right. Then the next one, which of the following statements is correct with regarding to the boiling points? Now, boiling points means that 3. What is the theory? Intermolecular interactions, molecular weight, and surface area, right? So N2 and NO. First, we'll consider the intermolecular interactions. This is polar, this is non-polar, right? So it is having a zero dipole moment. This is having dipole moment. So which one is having greater boiling point? This is having a dipole moment, means this is having dipole-dipole interactions. This is having just London forces. So dipole-dipole interactions are stronger than London forces. Therefore, the first one is correct. First one is wrong. Okay. PH3 and NH3, which one has a higher boiling point? This one has hydrogen bonds. Why? Because nitrogen is more electronegative atom. So nitrogen and hydrogen with another molecule, ammonia molecules, hydrogen, it can form a hydrogen bond. So ammonia has hydrogen bonds. This one has dipole-dipole. Therefore, PH3 has higher boiling point is wrong. Why? Because hydrogen bonds are stronger than the dipole-dipole. Hydrogen bonds are there in ammonia. Therefore, it is having a higher boiling point. Okay. And then xenon and krypton. Xenon and krypton. When we go down the column, atomic radius increases. Atomic radius increases means surface area increases. Therefore, xenon is having greater boiling point than krypton. Okay. So that is a correct statement. So what is the answer? Answer number 3. We'll just check this two also. Has a higher boiling point. So wait. This molecule has a greater surface area than this molecule. So this is wrong, right? And this is again wrong because chain molecule is only having greater surface area. Therefore, that is only having the higher boiling point. So what is the answer? Answer number 3. Okay, the last question for today. Select the correct statement. Okay, select the correct state. The electron pair geometry and the shape of SF5 plus. Okay, SF5 plus. What is the skeleton? SF5 plus. This is the skeleton. Electron pair geometry is trigonal bipyramidal. Why? Because there are 5 repulsive units. Are there lone pairs? No. Then will the electron pair geometry change? No. Then the shape is equal to the electron pair geometry, right? So the first one is a correct statement. And when we compare the atomic radii, positive atoms are having smallest atomic radii, negative atoms are having greater atomic radii, and the neutral atoms will be in the middle. So it will be like this, okay? So that answer, first one is a wrong statement, okay? Electron pair geometry and the shape are similar. Here they are saying different, no, so it is wrong. This one will be correct, okay? The number of resonance structures for HNO3. Now you just draw the resonance structures. Number of resonance structures. They are not asking what is the number of stable resonance structures. They are asking the number of resonance structures that can be drawn for nitric acid. One is unstable, but we have to count that also. It is a resonance structure. So there are 3, not 4. So that is wrong. Carbonate has the longest carbon-oxygen bond among the molecules, this and this. Okay. Bond length means you have to compare the resonance hybrid of the carbonate, okay? And always triple bond is having a greater bond length. I think I explained that in an earlier question. So you can refer to that one's explanation as well for this, okay? The bond length. Sp is having the lowest bond length than sp2. And sp2 is having lowest bond length than sp3. Right. Among the molecules, the electronegativity of carbon atom increases in the following order. Sorry, I showed this explanation, right? I'm sorry. Now only we are coming to the electronegativity. So what is the first factor of electronegativity? Hybridization of the carbon atom. So here what is the hybridization? S1, 2, 3, sp3. S1, 2, sp2. I said for hybridization, count sigma bonds and the lone pairs, sp2. And here sp, sp. So this is how the electronegativity will vary depending on the hybridization. So what is the answer? Answer number 5. Answer it. CH4, COCl2, HCl. What is the answer? Okay. Wrong statement. This one. This is wrong. Okay. Magnesium 2 plus is having the lowest radii. No. This is correct. Answer number 5. Okay. So we are done for today. Did you all understand? Can I have a feedback of the session today? How did it go well? What was there any bad things about the session? Let me know your honest feedback, please. So then I can improve in the next. 20th question is not clear, okay? I don't have time to explain it now. So we will meet in the next session. If you all have doubts, I'll try to clarify it through the group, okay? So how was the session? Was it good, bad? Give me your honest feedback, please. Yeah. Okay, if there's anything to clarify, okay, send it through the group. Please, okay. Okay. Thank you. Okay, thank you so much for joining for today's session. I hope you all got the maximum benefit out of it. So it's okay, thank you. It will be helpful for the time management during the A-level paper. So if there's anything to clarify, you all can ask it through the group. If I can, I will answer it. And thank you very much for joining today's session. Okay, bye.